Well, hello, everyone. So I'm very grateful to have the chance to speak with you today about QUIC. The presentations I've seen so far have been very interesting, and it's really great to see this work going on. So, as Robin mentioned, I'm a software engineer at Apple working on our networking team on the client OS. So I work on that networking stack, all the kind of the different layers from IP up into HTTP. And this is an area where integration of QUIC has been a key feature that's been in the works for many years for us. And so today I thought I'd share some thoughts from our experience of supporting QUIC specifically in the client OS and how it's enabled new features for us. So QUIC, well, it's only been in the past year that it's been official RFC and done. It's been gradually changing the shape of the traffic on the internet for many years already. We all know that. But still, QUIC has been used mainly for just a couple of use cases. And so when we ask the question, who can use QUIC today and what traffic has already been using QUIC, it's mainly web browsers, right? Web browsers are the original use case, and they're still the dominant case if you look at traffic patterns today. And from an operating system perspective, web browsers are just one type of app. But these are particularly big apps that generally ship with their own homegrown networking stacks. And thus, these are people who can afford to do the development work to integrate this new protocol paradigm and figure out what it means for them. But browsers just represent one kind of many different kinds of apps that run on a client-facing operating system like what we do for Mac OS and iOS. And many app developers don't have the resources to build their own networking stack or integrate a third-party SDK. So the lowest common denominator for usability is what's built into the standard libraries, what ships with the OS. And so that's what we are trying to solve. And so to allow QUIC to be truly ubiquitous, it needs to be just as easy to adopt and to use as TCP and raw UDP have been. And this is one of the goals we've had, to bring the security and the performance of QUIC within every developer's reach, and thus within the reach of every user. So you get a QUIC, everyone gets a QUIC. That's what we want to see. So when we ask this question, what needs to happen to make QUIC be really ubiquitous? And overall, it needs to be treated as a first-class protocol in the system, just like TLS and TCP. So what are the things we need to do? Well, first, QUIC needs to be deployed on the servers, and that's largely out of scope for what I want to talk about today from the client perspective. But I thought it was important to acknowledge that any work that is done to make clients speak QUIC only matters insofar as you have servers to speak it to. Second, we believe that developers need some system default APIs through which to use QUIC, like they've had for TCP and UDP since sockets came about. And they've had that for TLS and HTTP for quite a while too. Most kind of OSs have some basic support for that. Third, QUIC needs to be really efficient. So it's great if QUIC can perform well over the network, but if the cost of handling UDP system calls directly in your app slows down your phone or drains your battery too quickly, it's not going to be worth it. And last, the transition to QUIC only works when you have a seamless way to fail over from QUIC to other alternatives or between different QUIC alternatives when you have impairments on the network. All right, so first, we think it was important to look at APIs. And to make QUIC as accessible as possible, we believe it is important to make this a system-level networking API that's available as part of the standard HTTP APIs. On our platforms, it's called URL session. But as well as that, the transport connection-oriented APIs, for us, that's called network framework. So QUIC is, of course, really easy to adopt if it's part of HTTP3. every major HTTP framework out there should be supporting HTTP3 and QUIC. If you haven't done it already, please do it. But for QUIC to be available for any developer of any type of application, it needs to be available directly, not just within HTTP. And it's not immediately obvious what the best way to expose raw QUIC is. This is something that, as a community, we still need to come to consensus on. And the way that we ended up doing it for iOS and macOS was to represent the API with two concepts: a QUIC stream, which was represented using the same byte stream representation that we use for TLS and TCP streams, and then the notion of a multiplexed QUIC connection, which we chose to represent as a group of streams. So just as an example to see how this works, each QUIC stream can be used with what our framework calls a connection object. So if you look at how this works for a TLS connection, you can create a connection to example.com port 443 using TLS, and that's all you have to do to create a TLS connection in kind of the standard networking library. To do QUIC, we believe it was important. There's only a slight tweak you need to do to the object initializer. Instead of using TLS, you say you want to use QUIC. And one of the other things that came out was you have to always specify an ALPN now. But if you do that, that is sufficient to be able to translate your TLS code or TCP code into QUIC. After that point, you can use exactly the same code to send and receive bytes, to look at metrics about your connection, to close the connection, do all the basic machinery. And we believe that's really important to make this adoption work as minimal as possible. Now, you may be asking how this works with a multiplexing protocol, which is what QUIC is. It's not just one stream. So, in the naive case, if the app doesn't do anything to be aware of multiplexing, we decided it makes sense to say the system will automatically multiplex streams for the same server using the same protocol. But of course, apps, a lot of apps will want to be aware of this. And so if they want to manage QUIC connections and multiplexing, we use a connection group concept. So the outbound client-initiated streams can be pulled out of a group and say, hey, give me a new stream off of this. And inbound streams can be delivered just as an event on that group. So this model has made it already very simple for apps to adopt QUIC, and we've seen people internally and externally using it. So I strongly encourage any other APIs or systems that have generic networking libraries to make it just as easy to extend from TCP and TLS to go to QUIC. This is a discussion we're having within the TAPS working group, in IETF and other places. But it's something I think the broader community needs to think about of how are we migrating. So the other big challenge for the client OS is to make QUIC efficient. And quite simply put, this means reducing the overhead of UDP sockets sending and receiving tons of little packets. This is something that TCP sockets got away with because they were dealing with big chunks of stream data instead of individual packets. The problem is mainly in the cost of context switches and copies, where each incoming or outgoing QUIC packet requires a new system call and a new data copy. And for bulk data transfer, this cost really adds up. So if you work on a server implementation, you know all about this overhead already, and you have your own solutions, but it's a real problem for clients too. So when we looked at this, the two options were to either try to make UDP sockets more efficient, try to make them have a batch copy mode, like a multiple read and write, or to pivot to a different type of solution, like a memory mapping solution. And luckily, we've been running with a user space networking stack for several years on iOS specifically. And this last year, when we released QUIC as a system API, we decided to also enable that user space stack on macOS. And so now it's available on all of our platforms by default. This is the way that everything works if you're using any of our networking system APIs. So this is a system where UDP and IP packet processing is all handled inside the user space process, not inside the kernel. And the kernel presents just a memory mapped ring of packets to the user process, and the kernel just, all it has to do is correctly categorize packets that are coming into the correct process and then signal, hey, there's something to read on the ring. Kind of looks like this. You have just a bunch of slots within a ring that you can access from user space without having to do new system calls. It's just shared memory buffer. So when new packets are available, the library running in user space gets woken up if it needs to, and it can look at the available packets, and without needing to do extra copies or system calls, it can actually process the packet headers and do the decryption right in place in a large batch too. So just to show kind of the impact of this, I ran a quick test. This is just at home. I grabbed an iPad running a Wi-Fi at my house, and I read like a speed test download type load over QUIC. And I did the same run twice, once over sockets using our QUIC implementation, and once with the user space UDP and our QUIC implementation. And the biggest difference by far was in the number of system calls that we needed to make. During the download, the socket side needed 35,000 system calls per second, and the user space UDP side needed only 15,000 system calls per second. This is just kind of for the whole system, kernel and user space all added up together. And that is 57% more efficient. That's, big difference for CPU, battery life, et cetera. And as a consequence, the throughput that we had, if you look at the stack using sockets, it was only able to achieve 75% of the throughput that we got with user space UDP. So this makes a difference not only to system efficiency, but really user perceivable performance. So if you're running QUIC client code doing large data transfers, be conscious of this, not just on your servers, but on your clients. And if you're on iOS and macOS, you can use the APIs we have to access user space. And if you're on other platforms, I encourage everyone to look at solutions that can use memory mapping. The last OS level change I wanted to mention was automatic failover, or making apps that adopt QUIC resilient to network conditions. So first, there's just the simple matter of being resilient to when DNS returns multiple options. I'm talking about happy eyeballs. So this is defined in RFC 8305, which is about racing connection attempts to v4 and v6. So many stacks already do this automatically for TCP. But traditionally, UDP was always harder to do this with because it's connectionless. How do you know how to race connection attempts? When are you done? QUIC, though, is a perfect candidate for using happy eyeballs. And I just want to encourage everyone, it should be part of every client QUIC stack. And another subtle point to note is that happy eyeballs uses historical RTT data, at least on our platform and a lot of others, to influence timing. And so this means also that if you have any metrics on your system about historical RTT and performance on different links, you should start splitting QUIC out as its own category separately from UDP and TCP, because it does have its own information, and that should influence future behavior. And the other more interesting case is how to handle networks that don't work well with QUIC, of course. And I like to think of this as just another connection attempt race, just like happy eyeballs, but for different protocols. And presumably, this will often be QUIC racing or failing over to TLS and TCP. And of course, you could view this as HTTP 3 failing back to HTTP 2. But if we're looking at a future where QUIC becomes more ubiquitous, I think the difference is at a lower level than that. Which transport comes up first, along with the ALPN it negotiates, will determine the application protocol that you end up using. And the detection of brokenness for QUIC and any heuristics you have and statistics about what was the optimal way and the optimal timing, I think that's best shared at a system level such that it's not only benefiting the HTTP3 applications. So I think this is kind of an open area still. There's an interesting question that I think is yet to be answered around how non-HTTP applications that use QUIC will evolve and how they want to handle failover at this level. So as we look at system APIs and support for this type of thing, This is one area I think it'd be great to hear input from new applications, non-HTTP applications over QUIC, and see how they want to use this functionality and what their failover patterns would be and how they can benefit from kind of the system knowledge and intelligence around when QUIC is working and not. All right. So far I've talked about just enabling the use of QUIC in the client OS. And it's great for the system to support QUIC natively as a first-class protocol. But as I mentioned earlier, this still relies on server deployment. And in some cases, applications changing their code to adopt new APIs. So, can we go further to try to see how do we get to everyone using QUIC sooner? So I wanted to mention one way in which client OSs and apps can start using QUIC more and sooner, and potentially use it for any kind of traffic at all. And what I'm talking about here is using QUIC as a proxying protocol, using Mask, and this is what we heard about in an earlier talk. And Mask lets you talk to TCP servers over a QUIC proxy, UDP or QUIC servers over that proxy, or even arbitrary IP protocols. So it means let's put everything over QUIC. Why not? So iOS and macOS are already taking a first step in this direction. iCloud Private Relay and some related privacy features on the system are using Mask proxies to add privacy to user connections. And this was built by putting HTTP3 QUIC proxy support right into our networking stack as part of the base OS. And this means that these proxy connections are running directly inside apps. It's not like a VPN that's trying to go through some other tunnel. This is just now part of your app stack. It's just doing QUIC all the time. And the really cool consequence of this is that now we can see what the world looks like when a lot of traffic starts using QUIC. So right now, this service isn't doing everything. We're focusing right now on all traffic in Apple's browser, Safari, regardless of if the web server supports QUIC. It's also used for all of our DNS traffic and any insecure traffic within apps. So without needing to wait for server or app adoption, we're able to start measuring and seeing what it's like to move traffic over QUIC right now. I want to point out another aspect of using a proxy that's very cool for performance, in which using Mask can allow clients to effectively fast open every single connection they make to a server. So here, if you look at this diagram, we have the client opening a new TCP TLS stream to an end server through what we have is this double hop proxy system. And even though we're going through two proxies, talking to a TCP server, we only have to wait effectively one client round trip plus any TLS processing time to complete a full end-to-end handshake for TLS. And that's because we can perform DNS on the egress proxies. We do the TCP handshakes on that side on behalf of the client, and those round trips are completely hidden from the client. And we don't need to spend the time on what is usually this slower last mile to the client. So, even if we have the path may take, a little bit of extra time, we're able to shave off the number of RTTs. So, overall, QUIC is a very useful protocol for communicating with a proxy. Just some of the benefits here, one, it's always secure. It uses TLS 1.3. This is already way better than SOCKS proxies and most deployed HTTP Connect proxies, which are not secure. And second, since it's multiplexed, you only need to set up a connection once to be able to connect to many, many different servers. And third, QUIC can support a mix of reliable and unreliable proxy traffic, as we've heard about earlier with datagram frames. And so this makes it perfect for talking to QUIC or UDP servers through the proxy, including making this chain of QUIC proxies like what we're doing. We're always going through two QUIC proxies, but we essentially don't have to feel that overhead because it's all just a pass-through there. So compared to SOCKS or normal HTTP Connect, there are really clear advantages. HTTP2 proxying has some of these properties, multiplexing and security, but it isn't quite as good. It has a lot more overhead of re-encapsulation. And if you compare mask proxies to a traditional VPN, like an IPsec VPN, again, the mask proxies really shine. Because you're doing this application level proxying or transport level proxying, you can reduce the DNS overhead. You can cache that at the proxy server. You can do TCP, essentially fast open all the time, like I mentioned before. Everything's running with quick congestion control and loss recovery, which you don't normally have with an IP level VPN. And QUIC can efficiently extend to support multiple hops, which is a lot better for privacy. So getting into some measurements here, the benefits of using the QUIC-based proxy are really clear if you just run like a page load test. And so that's one of the reasons we're focusing on these type of protecting browsers to start with. So these numbers, this is just an example that I ran at home Wi-Fi on my MacBook Pro, and I just loaded CNN.com once with our proxies and once without. And a site like this, CNN, has many different sub-resources, loads lots of different videos and images, and like declaring that the page load is complete takes a while because it has to do a lot of different things. And what you'll see here is that both the initial load and the overall page load time are noticeably faster when using our QUIC-based proxy. And so it's like almost twice as fast for doing just the DOM tree load, and it's a couple seconds faster for the overall page load. And it's shocking that I'm going through two different proxies and it's way better as a browsing experience. And so part of this is due to that reduced connection setup overhead I mentioned. That's just a way in which proxies can win. But it's also in part due to the fact that now we are using QUIC for all of this traffic. People use the internet on very imperfect networks that have loss and delay, and QUIC is better able to recover and handle this loss and the slowdowns. And this is just one example that you could reproduce on your own network, and if you want to do your own measurements. But we do see it backed up when we look at aggregated numbers from across the world. This is the type of experience that people are going to be getting as they start moving traffic over to QUIC. I also wanted to share some learnings and thoughts that we've had through using QUIC as a proxy at this scale. QUIC proxying has very different dynamics than using a QUIC connection to talk to a single web server. We hit very different limits than we would otherwise. And so as the people here work on their QUIC implementations, I just wanted to bring up these types of edge cases, and hopefully you can think about these as you're working on the scalability and performance of your QUIC stacks. So first, we're often dealing with much longer connection lifetimes. Since everything in an app can multiplex together, we're often leaving a single connection open for more than 15 minutes. It can be half an hour, it could be quite long. And we're also seeing far more streams being used over the lifetime of connection into many, many thousands that are running in parallel then over the course of the connection. Yeah, I mean, you're easily, you can get to 10,000 quite quickly. And since Connect and Connect UDP streams, when you're using them in Mask, they map to end-to-end connections. Each stream can also hang around for a very long time. So oftentimes, if you're going through like a browser, many of them are short, but you can have very, very long-lived streams. So at these scales, the scheduling of your stream data and how you handle, I have 500 open connections and I need to send data back, like it matters a lot. So, the more we can do tests at this scale, the better prepared we're going to be for different types of use cases. All right, so to wrap things up, QUIC is really changing the internet, and it's making a big impact on client OSs now. And this is one of the biggest changes that we've seen in these stacks in a long time. And we're only just now starting to see how apps will start using QUIC, and I expect to see a lot of innovation around it, and we'll have to learn a lot in the next couple of years. Proxying with QUIC and using Mask it's a great way to start using QUIC for more traffic and to learn about how a QUIC primary internet could look, and get a kind of a glimpse into that type of future. And then the kind of the question I'd like to leave us with, and hear your thoughts on is, how are our systems and our networks going to change, and how are they going to look as QUIC becomes more and more prevalent, and more prevalent than TCP eventually? Like, what is this future going to look like? What do you think we need to do to get there? And that's all I have. So thank you very much.
No, thank you for that very, very interesting keynote. You touched on quite a few points, especially with the mask setup, that I haven't even considered how much it could actually improve, like you say, the performance, even though you're jumping through different proxies. And the fact that you can enable this transparently or semi-transparently for any iOS app is, of course, amazing. So people, if you have any questions for Pauly, please let us know in the chat, or as Mirja is doing, raise your hand so you can ask a question. So let's go, Mirja.
Thank you for the talk. Of course, I have a question on mask, right? Or on the proxy setup. So you showed this data where, like, on your just anecdotal data measurements on your home network, you saw some improvements. And I know that some of my colleagues also just did some enabled private relay and looked at some of the delay data. And they saw very different results depending on which network they were logged in or where they were located or whatever. So I guess, like, there's a big impact on where the proxies are located, right? Can you tell something about the current setup and how this is handled? Sure.
Yeah, I mean, certainly the deployment and availability of proxies to you matters. I think right now the footprint of our proxies is, quite good. It's usually pretty close to people that are deployed on, what you'd expect as like the edge network. But a lot of it does matter. Yes, you have to select kind of an optimal proxy endpoint too, so you're not accidentally going all the way around the world. That does matter. I think, again, it's possible to see different results with different types of workloads. Like if you're looking at just a large throughput download, like a speed test over this, that type of measurement is going to look different. We're not able to yet do magical things to just make your link bigger than it really is, and so you may see overhead there. Where we generally do see good benefits is the type of load I'm talking about, in which you're just loading a page. And so I don't know if people were looking at that, because when you're opening up new connections, then you do see the benefit of multiplexing and connection reuse really add up. For the throughput case, I think it'll be interesting to look at ways that things like multipath QUIC in the future could help do better bandwidth aggregation or use of multiple links to improve how mask proxies can work.
So I think they did some throughput tests, but also just use it for browsing or whatever. But like where they saw big differences was in the round trip time, in the latency, depending on which network they were connected, and that was quite surprising. But we can discuss it.
Yeah, that'd be good to hear. Yeah, I mean, sometimes, depending on networks, just like the GeoIP mappings of cellular networks sometimes is quite inaccurate.
That might be a reason, yeah.
All right. Other questions?
Yeah, we have one in chat from Timo, who gave a presentation on MTU earlier for context. So he asks, with longer connection times or longer persistent connections, searching for the optimal MTU or path MTU is more beneficial. Is Apple currently using PMTUD, or what do you use to discover MTU?
Yeah, we do support PMTUD on the client side. I can't speak for all of the server implementations. So we're using multiple different proxy providers here, and I think they're in different stages of being able to do path MTU discovery. On the client, we do it. One of the interesting things that you encounter, though, is when you're doing QUIC over QUIC, or even as we are doing sometimes talking to QUIC servers, quick over quick over quick, your logic around PMTU D has to change, because essentially what you need to focus on is just the link that's actually on the wire first, and let it kind of ramp up, and then that limits what the inner or tunneled QUIC is able to explore up to. So I think an interesting area will be, as Mask comes further along and people are doing more of this, having a good discussion around how PMTUD works over multiple hops is going to be an interesting area to figure out how to really best optimize it. So we're doing a basic version of it, but I'm sure there's more we could learn.
So if I interpret it for myself, you're potentially saying that you should delay PMTU D in the inner tunnels until the outer tunnels have had a chance to do it, and then
right, or essentially until the outer one has expanded its MTU, your inner one won't really be able to do the full correct exploration.
Exactly.
And so maybe it will do some, but you kind of need to re-prompt it to say, hey, my outer one has changed. This is a good time for you to also bump up your MTU.
That nicely comes back to the previous presentation, because there the question was asked, how often do you restart? And then the question was, well, why would you ever restart? PMTUs don't change, right?
Yeah.
So yeah,
very
interesting insight. I thought we had Alefia. Do you have a question?
Yes, I have. Thank you. So, you projected a little bit in the future and said this is going to be widely adopted once QUIC is widely adopted. If I understand this correctly, if I have my my Apple device, my phone, and let's assume all the apps have adopted QUIC, would one anticipate sort of a network ecosystem where essentially each app has a constant long-running connection with its end server at the other end, and then streams come and go? Or what, how, I mean, sort of it's more of an open-ended question. How do you anticipate, if there is a wide adoption of QUIC for all Apple, iPhone devices, all apps on it, what would the network ecosystem look like?
Predicting the future is always interesting. So I can just throw things out. I think we're going to see a variety of different types of applications, and the type of application you're doing really influences that lifetime and size. So we already have a lot of people are very familiar with the HTTP3 web browser connection, and that has like a lifetime similar to an HTTP2 connection. Maybe it's going to hang around for a couple minutes. And it's going to you have connections going to a lot of different places. As we're doing proxy connections, these are longer lived connections to fewer places. And so, if traffic goes over mask proxies a lot, you'll see a lot more long-lived connections in apps. That's what we're doing today. But I think, as we see, kind of what I was trying to predict is like, okay, maybe we're going to have more media applications, more just applications just replacing their existing TLS connections with QUIC. I think it's going to be a huge diversity of the number of streams they'll need, the lifetime, and that's good. And I think it's a call to us to not only just optimize the system for QUIC, but optimize our QUIC stacks for very different patterns to make sure that they work to a huge number of streams, very long-lived, very short-lived, and consider all of those cases.
Thank you.
Very, very interesting. I don't see any other questions. I, of course, still have some. Lucas asks, why does Mask hate multicast? Lucas, you should take that to the mailing list now. Come on. I of course have a few questions.
Please.
One of the first ones is about happy eyeballs and how you do that in practice. So now that I have the expert on that here, I wanted to share. I did a presentation a few years ago.
Cool.
On how I interpreted that. Right, if you do both QUIC and TCP happy eyeballs, and IPv4 and IPv6, you would get this kind of situation, right? So it's too much. And then if you do that, do you always do all four? How do you decide? And if you do this in collaboration with resumption and especially zero RTT, aren't you increasing the potential for replay attacks and that kind of stuff?
Mm-hmm. Yeah, definitely an interesting area. So, first, just to make the problem worse before we make it better, if you look at what we have in Happy Eyeballs v2, it's not just v6 versus v4. It's all of the addresses you get back in DNS sorted as a list with, maybe v6 at the top, maybe two v6 addresses at the top, then a v4 address, then another v6. So we often see, 10 addresses. So it's a long list, and then you multiply that by 2, and now you have 20 things. So it's certainly a reason that you should not have a fixed 100 millisecond delay on everything. That's not going to serve you well. We do actually discuss this a bit. So within the TAPS working group, we have an implementation guidance draft that talks about racing between protocols, and it talks about kind of this tree. And so rather than having a fixed list that you fall back with, I think the logic that we are doing currently, and that I'd recommend via this TAPS document, is you have different branching layers. So you say, okay, if I'm going to race QUIC and TCP, that's one layer of a tree. And then you have another layer for v6, v4. And so the branches of the tree can progress in parallel, right? So there's essentially a timer that you have for QUIC to TCP. And then each of those attempts can have their own sub timers. And so the timers actually can overlap, right? You end up interpolating these different trees if you look at it as a linear timeline. But I think that ends up not wasting too much time, and you explore the space of the tree more efficiently.
So the latency is not that bad, but you are still opening all these different connections and then abandoning 90% of them.
Assuming that they do not progress, right? Because you cut off the branches once one succeeds. So
yeah, sure.
Generally, if you've already waited enough time to try 2 or 3 different QUIC addresses and you haven't gotten anything back from any of them, it probably is a good time to abandon them and fail over to TCP.
That makes sense. Great. Then one thing, I still don't have a different question from someone else, right? I can keep going. Yeah. I find the API design that you chose a bit strange to me, because you go completely against the naming in the RFCs and the naming that a lot of other people are using and other documentation are using. And I wonder if that's not going to be confusing for developers, especially developers who are not QUIC experts, which I expect will be most of them, to make sense of what exactly a connection group is and how that maps to QUIC and all those things. Do you agree? Do you not?
I think it's an interesting thing to discuss, and it's some of these terms are the same terms that we have again within TAPS. If you were looking at things purely from a QUIC perspective, yeah, you have connections and streams, and that's how things are named. But when people are coming over from TCP connections and TLS connections, they think of those connections essentially as streams. So I think there's no good way to there's going to be confusion in one direction, either which way you go. And I think the naming ultimately matters a lot less than the shape of an API and how you hold it, and the fact that you can deal with abstractions in the same way. Maybe the naming would have been different if QUIC was around before TCP and TLS. We probably would have thought of things differently, but being able to say, I have a common way to send and receive data, I have a common way to open and close a byte stream is useful for being able to migrate code. And so far, like in the adoption of QUIC, we've seen it hasn't caused too much heartache, really. And it's been easier to move the code over.
Great.
But it's a good discussion to have.
Yeah, but we already had a TAPS discussion earlier as well after Nick's talk. So it remains like one of the big challenges, especially with these new protocols. Another thing we already discussed was Miria's talk about Mask as well. And she found in their implementation is that if you have multiple concurrent streams, their proxy would always send available data on one of the streams until that was drained, and then the second one and the third one. So keeping data back for all the other streams, which ended up causing the end-to-end QUIC connection to detect it as spurious loss because things were getting stuck in the buffers. And so she said we really need some kind of decent multiplexing schemes and decent prioritization at the proxies. And I wonder how did Apple tackle that in concrete ways, if you can talk about that.
Yeah, I mean, we probably don't have enough time to get into it all. I think this would be good discussions for the future. Again, we're using multiple different proxy vendors with different QUIC implementations. All I can say is, this is definitely something that came up with all of them, and figuring out how to tune that scheduling when you have hundreds of connections going in parallel, all with their own rate, and they're forwarding QUIC and TCP on the other side. It really matters. It takes a lot of tuning. But I'm not the expert on that. For the client, it's a little easier because if you are running the application, you know exactly when data is available to send. The hard work, as Mary was implying, is on the proxy. So
what I take from that
is
that
to teach us.
Yeah, but what I take from that is definitely something that has been optimized.
Yes.
Prior to private relay deployment. Yeah. Okay.
Yeah.
Excellent. Then I will pester you about that later.